large numbers and so on. Now, not to confuse things, but I will say that this is memoryless in time. I'm thinking of I as being a time index here. But if you wish, you could have written these channels side by side in space and then just used them once, where you send X1 into the top channel, you get Y1, etc., etc. And then you could achieve all the goals that you get from the asymptotic theory at time 1. This is done all the time in physics. If you do it in time, it's called the time average. If you do it in space, it's called the ensemble average, or in statistics language, the expected value. All right. Now let's have another definition. The information channel capacity C, maybe I'll put a C sub I, is given by the max over all input distributions P of X of I of XY. The mutual information between the input and the output. Now, I'll take the I off this in a couple of lectures because this is also what you might call the operational channel capacity, which is the embodiment of the top statement. It's the log of the number of distinguishable symbols per use of the channel. Okay, so now let's look at some examples. And with this sequence of examples, I'll reveal the whole theory, or why things are true. 1. We consider this channel where y equals x. You send a bit, you receive a bit, and C is the log of the number of distinguishable x's. There are 2 distinguishable x's. That's the rough interpretation, but we will do C is max I of xy. This is C sub I over P of x. All right. What is this? This is h of y minus h of y given x. Now, if I know x, I know y, so h of y given x is 0. So now I want the maximum of h of y over all input distributions P of x. So this is h of p 1 minus p, corresponding to probability x equals 1, probability x equals 2, which is equal to, which is less than or equal to h of a half-half, which is 1. The uniform distribution maximizes the entropy. So you get 1 bit. So this is equal to 1. We have just evaluated this. Now, speaking of hard ways to find the capacity of this channel, there it is. All right, 2. Let's look at this example. We have 2 inputs, 1 and 0. This is x. And here's y. 1, 2, 3, 4. What's the information capacity of that channel? Well, I of xy is h of y minus h of y given x. Let's see, what am I going to put here? Say 9/10 and 1/10, or 8/10 and 2/10. What's the information capacity of that? Well, that's sort of the messy way to write it. Let's try it this way. H of x minus h of x given y. This leads to an easier calculation. Because if I know y, then I know x. So this is 0. And h of x is less than or equal to 1 bit. And it's achieved by p star of x. P star of x equals 1 equals a half. So it's achieved by a half-half distribution here. It makes sense. If I'm sending a bit stream and you're understanding every bit in it, then I get maximum information through to you if each bit is a fair coin flip. The entropy is 1. Then the entropy of the string is n times 1. It's n bits. And notice that every string of x's I send through here can be correctly decoded by observation of y. So see this noise here? This noise didn't matter. And the reason it didn't matter is because these conditional distributions have non-intersecting support sets. So I can unscramble it. All right, let's look at number 3. Ow. Here we have 4 inputs. One, 2, 3, 4, and outputs 1, 2, 3, 4. Now I'm going to put half a half on each of these. I'm not quite sure yet whether I need to. So when I send a 2 with probability half, it comes through as a 2, and with probability half, it comes through as a 3. Now, what is C sub I here? Well, let's calculate I of xy. And that's equal to h of y minus h of y given x. Okay. If I know h of y given, if I know x, then y is either x or x plus 1 mod 4. So, and that's entropy of half a half. And that's 1 bit. Now, h of y I don't know because I don't know what p of x is. But I do know that h of y is less than or equal to h of a fourth, you know, the maximum entropy distribution on the alphabet of y, which is 2 bits. So h of xy is less than 2 minus 1, less than 1 bit per transmission or use of the channel. With equality equal if and only if p of y is uniform. And we can achieve that if p of x is uniform. Achieved by p of x uniform over the 4 possibilities. Also, there's another way to achieve it. Put mass half here, 0 here, half here, 0 there. In fact, we can distinguish 1 and 3 because the decoding sets don't overlap. We could also have distinguished 2 and 4. But, right. So now every time I want to send a bit, I send either a 1 or a 3, and they can't be confused by y. So C sub I for this channel is 1 bit, or 1 bit per use. This is like a noisy typewriter. Every time you type, you get the symbol or the symbol after it, or next to it on the QWERTY keyboard or whatever. So, number 4 reveals all. What about this? Well, C is max I of xy. This has crossover probability P, P bar, P bar. No mistake.